identify if A overgrows B, A overgrows B. And if they were really actively running around, you would think, but there's no way to know for sure, that this is bad. And so you would get out of the way. But there's some funny things that also don't make sense because there are cases of overgrowing. I have a beautiful specimen of an overgrown Edrioasteroid that looks like this. There's a big guy coming over it, sort of like, you know the movie Independence Day and the spaceship's coming over? It kind of reminds me of that. And then there's this little tiny Edrioasteroid just peeking out underneath. And all that's exposed is that much tip of one ambulacrum. The hydropore's covered, the mouth's covered, the anus is covered, and it's a fully articulated Edrioasteroid that's completely incapable of existing. Now Dave did some of the early work on what we call taphonomy, which suggests that a dead echinoderm could only live for just a couple days. So what is this telling us? It's hard to say. Because it's hard to know, I mean, this would clearly get out of the way if it could, but it probably wouldn't be very happy in this situation either. Bottom line is, I don't know.
Everything about that picture looks to me like it's something that was capable of grabbing the crinoids and moving. And the one I have that I think you've seen, you can see on the it gives me that same feeling.
But you know, to me, I don't see that at all.
You don't see that.
Because that one in particular, what it looks like is it's just sitting there on the stem. And I'm not sure why that would suggest it moves or doesn't move. That particular one I don't think says anything. But these high density things very strongly have these very strong overgrowing things and fighting with everything.
I've seen time-lapse movies of starfish on the ocean floor, big masses of them. It seems to me, I can't remember for sure, but it seems to me sometimes they like to climb over each other and stuff.
Yeah. But again, these aren't those sort of animals. These are, ecologically, these are barnacles. Yeah.
One thing that brought to mind for me was in the whitewater area in Brookville, I've seen Edrioasteroids where some of them were like this, some of them were like this. So they didn't always necessarily stick to what they were on. At some point, some of these had become dislodged.
That can happen occasionally. More often than not, if you look at those very, very carefully, you'll see that they're probably attached to mollusk shells. And the mollusk shell itself will dissolve away, leaving the inside exposed. Sometimes you'll see, for example, you'll see an Edrio on a mollusk shell, and it's upside down but completely in contour with the shell, which indicates the Edrio was on the inside of the shell. The shell dissolved away, exposing the Edrioasteroid. I've seen that a lot of places. Or Edrios, in a lot, I've seen places too, like at Trammell Park, you'll get them with an upside down one and a right side up one like that, from the same situation.
Trammell Park. We talked about the fluvial basins on the Edrioasteroids. Now, I'm not sure I followed that correctly, but these fluvial basins are what we normally think as the bottom of the Edrioasteroids.
Yes, it's in the.
So why do they have two feet if one's going to move at all? Seems like it'd be kind of redundant.
Because 2 feet aren't made for moving. They are a feeding structure. And in starfish, okay, in the grand scheme of echinoderms, there's only 2 modern groups of echinoderms. Crinoids and all the other groups of echinoderms are a little tiny group of echinoderm diversity. The problem is when you look at an echinoderm from a modern perspective, you think sea urchin, you think starfish. Those are the wacky ones. Normal echinoderms are things like crinoids, Edrioasteroids, and a bunch of the other groups that you've never heard of.
In those, the 2 feet just line.
And in all of those, the 2 feet are nothing but feeding structures.
But in starfish, they are for.
They've been co-opted for that, but they also are involved in the feeding and in respiration. So what's actually happening in most echinoderms is you'll have, I'll just draw a very basic starfish. You'll see a little, very primitive starfish. You'll see a divot like that. There's a thing called a radial canal that pumps water up and down the arm. There's a little canal like that that pumps to a little podial basin here, and the tube-foot sticks out like this. Sometimes those perforate, or sometimes there's a hole and they go through, sometimes they're just a pit. But you squeeze that, the tube-foot extends, you relax it, it contracts. The problem is in isoprophids, they've never been recognized, because if you look where they normally lie on the floor plate. But what's happening in the Edrioasteroid is we don't know where the radial canal is. We haven't identified it. But if it's in the base of the food group, which seems likely, this canal extends up the side into a hole here between the cover plates, and those pits sit there, and then the tube-foot can extend inside like that.
So if you take the side that you think that the Edrioasteroids were mobile, if the two feet don't move them, what?
If you take the side that the Edrioasteroids are mobile, the 2 feet have nothing to do with it.
Well, what mechanism would them?
It's probably something like an anemone where it just sort of scooches along. But the 2 feet are on the wrong side. The 2 feet are the upside. That's normal in echinoderms.
Well,
2 feet down is abnormal in echinoderms.
Well, that's what I was asking about the podial basins. On an Edrioasteroid, they would be sending the 2 feet up.
Yeah, the 2 feet will always go into the ambulacrum.
So, I'm still having a hard time imagining what can, if they were mobile, what can,
Yeah, the bottom of an Edrioasteroid,
something.
the very earliest Edrioasteroids, the bottom surface is just a row of plates, like, just completely covered. Those plates go away, and it's just a fleshy pad on the bottom that is never preserved.
There could just be some sort of muscular
Something.
crawling.
Yeah.
But like the whole flipping of that thing, it's like it's really exciting if the Edrioasteroid is their relatives, and if it's stationary, can't move, and that these things you say were co-opted to help in locomotion, that's amazing.
Yeah, I mean, there is something alive today that looks very much like an Edrioasteroid, and it's a type of sea cucumber called a Colin. And what they do is they actually are oriented not up and down, but they're on their side, and they have 3 rows of tube feet on the bottom surface, and they use that to crawl along. And even those move, you know anything about those? There's something like they only move like a centimeter a year if you push hard. But they sit there like barnacles. They don't do much. I mean, I have no problem. Clearly, if an Edrioasteroid is growing across the substrate, there is motion involved. So to say that they do not move would never be correct. But the question is, how much do they move? Are they actively running around? One of the things is you occasionally, very occasionally, find an Edrioasteroid not attached to something. But does that mean it was caught in the act of moving, or does that mean it was sick and fell off?
Well,
But that's incredibly rare.
Don't Smith and Paul contend that cyclocystoids were mobile?
Smith and Paul have cyclocystoids reconstructed with no coelom. In other words, there's no gut cavity. You open the top, you open the body, you look through.
Well, they have 2 layers of plates.
Yeah, but they reconstructed and pressed together with no body cavity. Look at the picture, it's awesome. Cyclocystoids are probably, if related to these, very distant.
I noticed that Cambrian thing had some similarities to cyclocystoid, at least with the marginal plates.
But they all have marginal plates to some degree or another, so do starfish. The Cambraster thing actually